All right, so what we want to have a look now is more of a mechanics kind of thing, and where our particle could be in motion, okay? And I guess the fundamental principle that we have in play here, and it's always the same, is if our particle is in equilibrium, we're saying that the sum of the forces is equal to zero. In other words, all the forces are cancelling each other out, and there's no motion, there's no movement. In reality, what we're saying is there's zero acceleration, okay? So if our particle could theoretically be moving at a constant velocity, okay, so there's no braking to slow it down, there's no acceleration to speed it up, there's no force causing that change, well then again, the sum of the forces is still zero, all right? So what Newton's laws of motion tell us is in actual fact, the sum of the forces doesn't equal zero, the sum of the forces is equal to mass times acceleration. So if my acceleration is zero, well then by definition or default, the sum of the forces is zero, okay? So that's the fundamental principle of all our forces, mechanics, statics principles. I'll probably just repeated myself, is that the sum of the forces equals ma. That's always our starting point. And of course, if our particle is stationary, that makes the sum of the forces equal to, where the mass is in kilograms, acceleration is in meters per second squared. And typically we work with the forces in newtons. So this is where we will double up a little bit because we're looking at some of the year 12 content. One kilogram weight is the same as 1 G Newton, where G is the force due to gravity. Okay, so whereas we might write a particle with a weight of 5 kilograms has a 5 kilogram weight acting, the equivalent units is to say it's got a weight force of 5 Gs. Okay, where G is equal to 9.8 meters per second squared. That's the acceleration due to gravity. All right. We will talk more about that certainly next year, and I'm sort of hoping we don't have to delve into it too much this year. The processes are exactly what we've been doing. Identify all the forces, weight force, normal force. If we happen to have any friction slowing motion down, tension in the strings, or we might have a pushing or thrusting force, all right? Clear diagrams, and then again, we resolve. And what we say is we resolve in the direction of motion or the direction of intended motion, which is why if we've got that particle on a plane, we resolve in the direction that the particle could move if it was going to slide up or down that plane. All right. So let's have a bit of a look. In this one here, we've got a box that's on the floor of a lift, accelerating upwards at 2.5 meters per second squared. The mass of the box is 10 kilograms. Find the reaction of the floor of the lift on the box. So step one, we draw a diagram. Okay, there's my lift, my lift in play. I've got my box. It has a weight force of 10 Gs or 10 kilogram weight. We'll keep the kilogram weight. And the reaction force or the normal force is N acting up. All right, acceleration of 2.5 meters per second squared. So my starting point is sum of the forces equals ma. So on the left-hand side, we concentrate on all the forces that are in play. So if I decide to make, since acceleration is upwards, I'll make positive as being up. So the normal force N is acting up. The weight force 10 is acting down, so it's subtract 10, and that's equal to ma, which is 10 times 2.5. Yeah. So now if I just rearrange that, they're the only forces acting. I don't have to worry about vertically. So N is equal to 10 by 2.5 plus 10 is 35 kilogram weight. All right. Now, I've modified this question to suit your workbook. Same sort of thing. A body of mass 5 kilograms rests on a smooth horizontal plane, is pushed by a horizontal force of 20 newtons for 5 seconds. Now, how far does the body travel in this time? So what I haven't mentioned, and we're going to introduce back in here, is our kinematics knowledge. Yeah. Now, I'm thinking we've got kinematics knowledge. V squared equals U squared plus 2AS. S equals UT plus half AT squared. V equals U plus AT. So they're our main kinematics equations. And don't forget that they all apply whenever we have an environment that is undergoing constant acceleration. And if we have a constant force, we have a constant acceleration. So typically, once we have our particle is moving, the first step is to work out what acceleration is our particle now undergoing because of the forces that are in play. All right, so let's think about, again, starting point. Sum of the forces is equal to MA. We've only got motion in one direction, that's horizontal. So we've only got one force in play, and that's a 20 Newton force acting to the right, because I'm going to take that as positive. And that's equal to MA, which is 5A. Divide by 5. So in actual fact, our system is undergoing an acceleration of 4 meters per second squared, and it's happening for 5 seconds. So the time is 5 seconds. The particle was starting from rest. My acceleration is equal to 4 meters per second squared. How far will it travel? Well, if I use S equals UT plus a half AT squared, we work out that it will travel 50 meters. All right. Now, what's going to happen then is we're going to take away that force, and then it's going to slow down, which means we have another system or a separate system in play. And the only thing that carries over from that previous system, because my acceleration will change because I've got a different force in place, what will carry over is the velocity of the particle when I take the force away. So in other words, what is the velocity of my particle after 5 seconds? So V equals U plus AT, we start with zero acceleration. We start with 0 meters per second. We start from rest. 5 meters per second squared for 5 seconds means at the end of that 5 seconds of pushing, my particle is traveling at 25 meters per second. All right. Now, here's my force diagram for part B. Again, my normal force, my weight force acting down. Resistance, okay, is I've got 1.5 G there, but we're going to go back to our kilogram weight unit or measurement, just so we're consistent with our earlier stuff. And we'll just say there's a 15 kilogram weight force acting as resistance. Now, it could be friction of the table, it could be anything, okay? But basically, there's a braking force of 15 kilogram weight, all right? So we want to know how much further will the particle continue to move until it comes to rest, all right? So again, starting point always, sum of the forces equals MA. This time I've got a force acting to the left, which is a negative direction, because I've made to the right positive, equal to 5A, because they're the only forces I've got, which means my acceleration or deceleration is negative 3 meters per second squared. So that's now the new acceleration of the system. So if we want to work out, I've got an initial velocity of 25. I want to know when it comes to rest, so the final velocity is 0. Acceleration of negative 3 meters per second squared. V squared equals U squared plus 2AS. If I substitute that in and rearrange it and work everything out correctly, it will travel a further 104.17 meters. All right, so it really is a really big overlap when we start having motion between our kinematics rules and our forces knowledge. All right.